In this video, I'm going to demonstrate a method we created to identify homeless encampments from aerial imagery. This method was developed for the purpose of finding unhoused individuals in high fire risk zones that may not receive emergency assistance. We used imagery and an API from Vexcel Imaging, but the code can be adapted for other imagery sources as well. A couple of key components to this method are the GitHub repository for this project, where the Jupyter notebooks holding this code can be found, the GitHub repository provided by Vexcel Imaging, which has instructions for setting up your Python environment to be compatible with their tools, a .env file, which will hold your Vexcel credentials when you're licensed to use their products. Creating this file and saving it in the proper location are explained in Vexcel's setup documentation. And then finally, you'll need a shapefile of your study area. This can be created in ArcGIS Pro, and as you can see here, ours incorporates this area of the Santa Fe Dam open space in Los Angeles County. Once you are set up with the right environment, you can open up the code and start importing the packages you need. This is where you enter the file path for your .env file that was mentioned earlier. Your credentials are used for authentication, and you receive an authentication token upon logging in. After you log in, you can access Vexcel's imagery and import the necessary tools. Documentation for these tools is linked in the credits. The next step is to enter the file path for the shapefile you created of your study area. As previously mentioned, we used the Santa Fe Dam open space as our study area. This area has a high frequency of encampments and is located in a moderate to high fire threat zone. Note that you must export the study area as a shapefile separately for this to work. GeoPandas cannot interpret a shapefile from within a geodatabase. After you enter the shapefile, you can get the tiles that intersect the geometry provided. You can also set the zoom level here. So as you can see when I run this, the number of tiles that intersect this geometry provided is 404 at zoom level 19. This next block of code shows how to view an individual tile from that list. So first you enter the tile number to get the coordinates of that tile. Then you can copy and paste these coordinates into the getTile function. In order to visualize your tile of interest. And this is useful if you want to quickly view the effective changes you make to the method. There is an operationalized version of this code that loops through all the tiles in the study area, running the analysis without viewing single tiles and saving on processing. In order for tiles to be masked and filtered, they have to be converted to NumPy arrays. After the tiles are converted, the first mask that is applied is targeting shadows. Shadows in vegetation tend to lead to false positives, so masking them leads to better accuracy. And there's the result of that mask. After this step, the image array is converted to the HSV color space. And as you'll see in a second, this highlights brightly colored pixels against the background pixels, and there's the tent from the previous image. More masks are then applied to target the pixels of interest. In this method, we used ranges that we found to be common to tents. We were able to pick out these ranges using color picker code and pixel histograms. This next block gives you a side-by-side comparison of the masking process. Again, this visual is not present in the operationalized code, but gives a sense of what is happening. So as you can see, this is the original image, the shadow applied filter, and the result of all of the masks combined. After masking, the image is ready for blob detection. The parameters included here are the best we found for our particular use case, but they can be easily adjusted. So running that, you can see that it does locate the tent and puts a circle around it. The centroid of that circle then corresponds to the coordinate location of that tent. The code also puts all of the coordinates into a list, and counts the number of blobs. In the operationalized version, the coordinate list and blob count are updated for each tile in the loop in which tents are detected. The coordinates you get from the blob detector are pixel coordinates. Vexcel has tools that can convert these pixel coordinates into geographic coordinates. And as you can see here, the coordinates have changed. In the operationalized code, the final list of coordinates is exported as an Excel file into a specified location with columns for latitude and longitude. Please keep in mind that our method had high accuracy on sets of small tiles, but was less accurate across large areas. As you can see here, running it across the whole study area produced 696 blobs, which probably includes a lot of false positives. Further parameters can be explored to scale this method up in a more accurate way. The last step in our method is to simply import the Excel file of coordinates into ArcGIS and visualize as a heat map. And for us, this looked a little something like this. I hope you have found this demo useful, and please reach out to a member of this project team if you have any questions. Our contacts are listed here, along with the data sources and project partners. Thank you very much.